Hello and welcome back to Nunley Math. I am your host, Aaron Nunley. I appreciate you coming back and joining us again. We are working our way through our functions unit. This is actually part B of our introductory lesson. The other lessons started to get just a little bit tedious, a little bit long. I thought it'd be better to split it up into two videos. So hopefully you've just completed the first part and you are coming back to check out the second part of the video. This, I believe, is the slide where we left off. We were talking about what makes a relation a function, and you were working your way through several examples. If you're stepping into this video and you have not done that yet, you really want to go back and watch that video. Make sure you're understanding those ideas before we move on, because we are beginning with the assumption you are already up with us. So let's keep going. Suppose I'm given a relationship that is in graph form. Up until now, I've been giving you some tables, some charts, and some coordinates, and I've been asking you, are these relations functions? But you know, coordinates aren't always written for us in coordinate form, and sometimes they're given to us in graphical form. So I want to be able to look up here and see this graph has 2, 4, 6 points that are located on it. Can we look at this and tell whether we're dealing with a function or not? Some students are pretty good at looking at this and identifying whether it's a function or not. Other students tend to struggle with that. What I'm going to do is I'm going to show you the long way to figure this out first, and then once you've seen the long way, hopefully we'll be able to identify a shortcut that might be able to help make that job less difficult or tedious. So if I were somebody who struggled with reading graphs and I was trying to identify whether or not this particular graph illustrated a functional relationship, what I would probably begin by doing is going through and listing all of the coordinates. Notice this is the coordinate 1, 0, the coordinate 2, 2, 2, 5, 4, 1, 5, 1, and 5, 5. And I wrote those out here. Once you see the coordinates, it's pretty easy to go through like we did in the previous slides in the previous video, and it's pretty easy to go through and identify the domain. Remember, the domain is just those first values, 1, 2, 2, 4, 5, 5, and of course we only list each number one time. The range, of course, is the second values, the 0, 2, 5, 1, 1, and 5, and we list those, of course, listing them only once as well. From this information, we should be able to look at that graph and determine whether or not it's a function very, very quickly and easily. Can you do that? Well, from my coordinates, I can tell right here that 2 is matching to 2. 2 is also matching to 5. So if I were to grab my pen and I were to underline those two, that's a problem for me. That's a problem for me because this point right here and this point right here both have the same x. You have that 2 matching to two different things. You may have also noticed the same problem over here. 5 is matching to 1 and 5 is also matching to 5. This dot right here and this dot right here create problems because they both have the same x value. They both have a 5 for their x. Now that does tell me that this is not a function, but hopefully in seeing that illustration, you've been able to come up with a different way to tell that would not require you to go to all this work. I'm going to hold off on telling you what that faster way is for just a second. I want to come over here and look at the second graph, and then we're going to go back and talk about that faster method as it relates to both graphs. This one is a little bit different because in this graph on the left, I had specific coordinates that I could look at and say what the coordinates were, and I can say whether or not they have the same x. This is a little more difficult because there are lots and lots of values or coordinates that show up in here. Notice you have the coordinate 0, 1 right here. You have the coordinate 2, 2. You have the coordinate 4, 3. You have the coordinate 6, 4. You have the coordinate 5, 4.5. There are a lot of coordinates on here. Do you know how many there are altogether? There are actually an infinite number of coordinates that fall on that line. Because no matter what two coordinates you give me, I can always give you another coordinate that's in between. It makes it much more difficult to find the domain and range. So let's think about this for just a second. If there's an infinite number of values, I can't list them all. I have to come up with a better way to do that. Can you think of a way to list a range of values? Well, let's look here and see what's going on. If I'm talking about my domain, I'm talking about these x values. So let's go ahead and write the word domain here. Very important. That's the domain. And wow, that's sloppy. That's the domain. If I want to look and see which numbers are in the domain, I know 0's in the domain, 1's in the domain, 2's in the domain, 3's in the domain, 4's in the domain, 5's in the domain, 6, all the decimals in between there are in the domain. In fact, this graph starts, if I'm just looking at the x-coordinates, it starts here at 0, and it starts moving to the right, and it keeps going to the right. How long? Well, it's going to go on forever. That's what the arrow tells me. It says it keeps right on going to the right forever. Does this look familiar to you? It should, because we did a lot of graphing in our previous unit on inequalities. We're going to have to express this domain not as a list of numerical values, but as an inequality that describes every numerical value that will work. And here's how we're going to write that. This is something we refer to as function notation. Function notation. Now, it's going to be difficult for me to write this, but I'm going to do the best I can. Here's what this says. This first value says, or this first x says, all values of x. All values of x. I'm just going to write all x because this is going to be difficult to do with the mouse. All values of x are acceptable. This little symbol right here, that little vertical bar that looks like, kind of like part of an absolute value bar, is a symbol that means such that, or sometimes we use the phrase as long as, such that, or wow. Such that, I think I reached the end of my screen. There you go. Such that, or as long as, the x meets this condition. I can use any value of x I want in my domain as long as that number is greater than or equal to 0. That describes what I'm seeing here. Everything will work as long as it's along this side. Well, what about our range? The range is our y value, or our output value. That's this right here. I'm going to list this as the range. If I want to know what the range is, what I'm asking is, what values along the y-axis get touched by this graph? Well, notice we're starting at the point 0, 1. That's this first coordinate. And from there, we're starting to go up. This looks like at the point 1, 1/2, 2, 2, 3, 2 1/2, 4, 4, 5, 3 1/2, 6, 4, 7, 4 1/2. We're starting here, and the graph starts going up and up and up forever. Can you give that as an inequality? The range is any y will work as long as that y is greater than or equal to 1. As long as that y is greater than or equal to 1. Now I'm going to erase the ink on the slide so we can talk about this just real quick. Two different ways to describe the domain and range in graphical form. If you are given specific coordinates, you can just look at the coordinates and list them and then find the domain and range that way. But if you're given a line or a series of connected points that that's more difficult to describe, that's too many for you to list, you're going to have to describe it using an inequality. Did you figure out how to tell whether these were functions yet or not without going to all this trouble? We said before that 2 was a problem because 2 matched to 2 and 2 also matched to 5. Did you notice something about the points? 2, 2, and 2, 5? If you didn't, the same thing is true about the points 5, 1 and 5, 5. They're both on top of each other. They're both on top of each other. If you have 2 points that you graph and they have the same x, the dots are going to line up one on top of each other. That's a quick and easy way for us to tell whether or not our graph is a function. If our graph is a function, if we were to draw a vertical line anywhere along our graph, you would find that it would never touch 2 points. But we call this the vertical line test. If I can draw a vertical line and have it touch 2 points at the same time, it would not be a function. So over here in this graph on the left, if I take this red vertical line and I slide it across the graph, you're going to notice that it touches both 5, 5 and 5, 2. I'm going to do that again. You'll notice it also touched, right here, there it was, 2, 2, and 2, 5. If it ever touches more than 1 point at the same time, it is not a function. Let's look over here at the graph on the right, this continuous graph where you have the connected dots. If I were to do the same thing over here, notice that as it slides along that graph, it never, ever, ever touches that blue line in more than one spot at a time. That means this is, in fact, a function. Now, I know that whole slide is probably a little bit confusing. You might want to go back and watch it a couple times. But as we do more and more examples of these, I think they should make more and more sense. Can you tell me if these are functions or not? You might want to pause the video and take a look. I'm actually going to go ahead and go. This number 5, in fact, is a function. Every item in the domain matches to exactly one item in the range. I can tell that because if I try and draw vertical lines through here, it's never going to touch more than one dot at a time. How about 6? 6 is a function because if I draw vertical lines through here, it's never going to touch more than one item at a time. So every item in the domain matches exactly one item in the range. What about 7? 7 is not a function. In fact, if I draw a vertical line here, you can actually see where we get something like 2 and maybe 0.3. I don't know, I'm making that up or estimating that. And up here you get the 0.2, it looks like 5.9. 2 maps to 2 different coordinates or 2 different items in the range. So this is definitely not a function. How about 8? 8 is a function because no matter where I draw my vertical line, I will never cross it at more than one spot at a time. Here's another set of these for you. Try those on your own. First of all, are they functions? They all are, in fact, functions. What I'd like us to do here is I'd like us to practice finding the domain and range. If I look at example A, you'll notice that these are discrete or distinct values. All I have to do is pull the x from each of those to find the domain. So if I look where this is on the x-axis, this is the point -3, -2. So this -3 is going to be in my domain. This is the point -1, 0. The x part of the coordinate is the -1, so that would be included. This dot is above +1. This dot is above +4. Your domain here is above +3. Your domain here is -3, -1, 1, and 3. Let me go back and erase those. Let's look at the range. Let's see, erase all the ink. The range deals with where it goes up and down. So if I look at this first point again, I'm just looking at where it falls on the y-axis. It's right here along the -2. This is along the 0. This one is along +2. And this is along +4. My range is -2, 0, 2, and 4. Now, if that's confusing to you, you can go back and list each coordinate, just like we did in the first slide. You can just look at all the x parts. You'll see they're the same. You can look at all the y parts to see that they're the same. I can do something similar to that on this slide. You will notice that this is a continuous graph because it has an infinite number of points that are all connected here. But notice, if you're looking at your domain or your x values, you can look and see that this graph begins here at -2. And it goes to the right, 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 and it continues going to the right until it reaches +3, at which point it stops. Your domain is all the x's that are between here. Can you write an inequality that gives you all the x's between here? This is what that's going to look like. The domain is all x's as long as that x is between -2 and 3. Notice I'm using a conjunction that we learned about in our inequalities unit that we just wrapped up. This conjunction is x is greater than or equal to -2 and x is less than or equal to +3. The range, on the other hand, deals with where this graph goes up and down. If I'm thinking about the y-axis, notice that we're starting here and we're going up, up, up. We stop going up, then we go up, up, up some more until we reach here. Your range is this set of values between here. It starts down here at -1 and it goes up here to +2. Can you write that as an inequality? This is every y will work as long as y is between -1 and 2. I'd suggest you pause the video, take a second, think that over, and try 9 and 10 on your own. I'm going to assume you've already done that, and then I'm going to go ahead and show you the solutions to these. For number 9, we're dealing with discrete points. There's your domain and there's your range. For number 10, you're dealing with intervals of values. Notice your graph starts here at +1 on the x-axis, and it goes all the way over here to +5. So your domain is all the numbers between 1 and 5. If you look at where it goes up and down, you'll notice that it starts up here at +4. It goes down to the 0. Then it comes back up to +4. 4 down to 0. Back up to +4. To express that range of values, we would say it this way. All y's work as long as y is between 0 and 4. That's a lot of information, isn't it? Let's wrap all this up with a couple last-minute things. This slide is designed to kind of pull together all the things we've learned about domain and range. When I talk about independent variables are another term we use to describe the x part of the coordinate. Or, if we have that collection of x's, we call that the domain. And those are all the inputs for our function. I've listed all these things together because these are words that mathematicians tend to swap back and forth between all the time without really making sure that students understand they all mean the exact same thing. I might even underneath here add the phrase left and right because the x-axis moves left and right if we're looking at a graph. I'm not going to do that now because it just takes too long to do that with a mouse, and I'm sure you have better things to do. When we talk about functions or relations, functions and relations give us a rule of some kind. And that rule takes these x's and applies a rule to them in order to give us our dependent variable, or our y or f of x, or our range, or our output. Notice I'm using lots of different words and symbols here, all of which mean the exact same thing. All of which mean the exact same thing. We're going to be given some kind of a value. That value goes into a rule or a description, and it outputs some other value. Let me show you an example of this. Suppose the equation y equals 4x plus 5. I'm going to circle that real quick. Represents the amount of money y that you earn for babysitting for x hours. This is the rule that's given to us. This rule represents the relationship between the amount of money y. I'm going to go over here and I'm going to put a money symbol. That you earn for babysitting for X hours. I'm going to go ahead and put the word hours over on this side. In the context of this problem, here's what we know. Hours is going to be our independent variable, usually represented by an X. The hours that I can use make up the domain. And I'm going to put those into my function or function rule. So the hours goes into the rule that's given to us. In this case, y equals 4x plus 5. And out pops the amount of money that I earn. Now, I say x is an independent variable because I can choose how many hours I work. I might work 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. I don't know. I can pick anything I want and put it in. But when I put the hours into my rule, the rule dictates how much money I will earn. That's why we say that y is the dependent variable, or the output is the dependent variable, or the range is the dependent variable, because the amount of money that I earn depends on how many hours I tell the rule to use. Okay. Let's look at this example further. This is the exact same information. All I've done is rewritten it. I'm going to ask a question based on it. So suppose the equation y equals 4x plus 5 represents the amount of money y, our dependent variable, that you earn for babysitting for x hours. Remember, we said x is the number of hours I work, and y is the amount of money that I will earn. Here's the question. If the domain of this function is 1, 2, 3, 4, 5, what would the range be? Remember that domain means a lot of things. It means the x value. So in this story, the x value or domain is going to be 1, 2, 3, 4, or 5. That means I will either work 1 hour, 2 hours, 3 hours, 4 hours, or 5 hours. 0 hours is not an option that's given to me because it's not in the domain. 4.5 hours is not an option that's given to me because it's not in the domain. 8 hours is not an option that's given to me because it's not in the domain. What we're told is if these are our only choices for the domain, for x, for hours, for our independent variable, they want us to find the range. Remember, the range stands for y, or f of x, or the output, or in this case, the amount of money. So this question is really saying, for this number of hours, 1, 2, 3, 4, or 5, what's the amount of money that I could earn? All I'm going to do is take my rule, which is given to me right here, and I'm going to stick in each of these values. I'm going to stick in a 1. I'm going to stick in a 2. I'm going to stick in a 3. I'm going to stick in a 4. And I'm going to stick in a 5. I'm going to take every one of these values, put it into my rule, and it's going to spit out the amount of money I earn. So if I worked 1 hour, I'm going to earn $9. If I work 2 hours, I earn $13. 3 hours, I earn $5, or $17, sorry. 4 hours, I earn $21, and 5 hours, I earn 25 hours. The domain was what went into the equation, or into the rule, or into the x position. The output over here is what y equals, or is your range. Your range is 9, 13, 17, 21, 26. The domain goes into the rule and spits out the range. The only possible values of dollar amounts that I can earn is $9, $13, $17, $21, and $25 because these are my only choices for the number of hours I can work. I'm going to do another one of these. That can be a little bit confusing. Suppose the equation y equals negative 2x plus 60 represents the number of gumballs left left in a machine. Notice that's listed as y. I'll come back to that. After X customers make a purchase. Now I want to know what the domain is, and in this case I'm not asking you for numbers, I'm asking you for the story. In the story, the domain has to stand for something. It's my X's, it's my input value, it's left and right on my graph, but in this story I'm being told that X stands for my number of customers. My number of customers. So I'm going to write that down. Customers. And I know that because I'm told it's X customers. What's my range value? My range value. Well, it says this rule right here represents the number of gumballs left in the machine Y. Y is my range, so my range must be the number of gumballs left. Now I'm going to abbreviate that and just write gum left. I would not do that in class, but there again, using the mouse here is kind of difficult. I would assume you're going to write that out all the way. It's the amount of gum that is left. If we assume the domain is from 1 to 8 customers, what is the range? Notice the domain is once again given to us. The number of customers is given to us. 1, 2, 3, 4, 5, 6, 7, 8. Now notice I did not use decimals because having half or 2/3 or 0.9 of a customer makes no sense in the context of this problem. So my domain is 1, 2, 3, 4, 5, 6, 7, 8. The domain goes into the rule and puts out the range, or the gumballs left. So I'm going to take 1, put it into negative 2x plus 60. Remember, this is my x. I'm going to put a 2 and put it into the rule. I'm going to put a 3 in the rule, 4 in the rule, 5 in the rule, 6 in the rule, 7 in the rule, 8 in the rule. Every value in our domain goes into the function, and it spits out the range. The range in this problem is 44, 46, 48, 50, 52, 54, 56, and 58. In other words, if I have 1 to 8 customers, the only possible number of gumballs that's left would be one of these. It would be impossible for me to have 30 gumballs left based on this rule. It would be impossible for me to have 100 gumballs left based on this rule. It would be impossible for me to have 42 customers or 42 gumballs left because I'm not allowed to have 9 customers. Domain connected to range by the rule. One last problem I want to give you. Suppose the equation y equals negative 2x plus 60 represents the number of gumballs left in the machine after x customers. It's the exact same relationship. But notice how I'm changing the question this time. How many customers? How many customers? Customers is y. Would it take to empty the machine? I just misspoke. I'm sorry. Customers is x. They're asking us to find the domain this time if they give us the range. What's the range value if range stands for the number of gumballs left in the machine and we're told the machine is empty? Well, if it's empty, there are 0 gumballs left. So I'm going to take my rule and I'm going to put 0 in for gumballs. My output or range value is 0. They want me to find the domain value. Well, this is just a two-step equation. You should be able to solve this without too much trouble. If not, you're going to want to go back and watch those videos. I'm going to do it quickly. Subtract 60 from both sides using the property of equality. Divide both sides by negative 2 using the property of equality. And you get x is a 30. If you have 30 customers, you will get an empty machine. Notice, by the way, negative 2 times 30 plus 60 would give me 0 gumballs. You got to be careful about which piece of information they're giving you. Sometimes they will tell you what goes into the rule. They'll tell you x and solve for y. Sometimes they'll tell you y and solve for x. So you want to make sure you read that very, very cautiously. I think I have one more slide here. Yeah, this is my Phantom Ghost slide I stick in here because it's Halloween. Hopefully that doesn't traumatize you too awful much. Once again, I want to thank you for taking the time to watch this introduction to functions and relations. I do realize it got a little long. It does have a part A and B. Make sure you watch both of those. But hopefully it will lay a strong foundation for you as we explore functions and relations more and more deeply. As always, make sure you like and subscribe. Leave us a comment in the comments section so that we know you're out there and listening. Make sure you turn on your notifications so that when we submit something new, you can be sure to see that as well. If you're interested in these slides, I am planning on making this slideshow available to you on Teachers Pay Teachers. So if you're a student that just wants to take notes as you follow along, you can grab that. Also, if you are a teacher and would like to use it in class, you certainly can download the slides there for your own use so that you don't have to remake them. Thank you again for your time. Best wishes to all of you. Take care.